I'm going to talk about sheath folds, and I decided to present you a wrap-up of all the stuff I did the last 2.5 years. And as there are some people which might not be familiar with sheath folds, I decided to start at the very beginning with what is a sheath fold. So, sheath fold is basically a three-dimensional structure. People say they are highly non-cylindrical folds, which is definitely true, but it's kind of hard to imagine anything with these words. So I personally prefer to call them cone-shaped. I mean, at least we have an idea what it looks, and that kind of resembles this cone-shaped structure of the sheath fold quite nicely. So sheath fold in nature look approximately like these. So that's a three-dimensional, very nice example of a sheath fold from Cap de Creos in Spain. And it's not very big, it's like this size. It's pretty small, but cute. That's a sheath fold which is very famous. It's in Ile-de-Croix in France. And it actually made it to a Nature publication at some point, a couple of years ago. So here you see the tip of the sheath fold. Here a part of it was broken out, so you basically see into the sheath fold. So unfortunately, these 3D examples are rather rare in nature. We see much more often, we see just 2D cross-section through these sheath folds. And we recognize them as sheath folds if the cross-section is basically across here, across the stretching direction of the sheath fold, because then we see these closed contours which are more or less characteristic for sheath folds. So that's an example from Oppdal in Norway, and that's very not well visible on this screen. I'm very sorry, but it's another sheath fold from Ile-de-Croix. Big one would look like the eye would be somewhere here. Anyway, so people did a lot of field studies on sheath folds, and they came up with classification of these folds. But just by looking at them in nature, it doesn't really give us much information about how they form. So people started doing experiments on them. And the first experiment has been done by Gobold and Gankis in 1980. And what they did was basically they used silicon. That's several layers of silicon. And one of the layers they were just indenting. And then they were putting the whole system in simple shear. And they saw that this dent in the layer got passively amplified and produced a sheath fold. So that is the cross-section across this experiment they did. And what they could observe are these closed contours here, which are supposed to be characteristic for sheath folds. They also had another idea that you can trigger these kind of folding when you have a very rough basement, and then you have a weaker layer on top, and you put it under simple shear, that this might perturb the flow enough to produce sheath folds as well. Then another very popular triggering mechanism was proposed, that you have a rigid inclusion, this black thing here, which is embedded in a matrix, and then again you put it under simple shear, and at the edge of this rigid inclusion you produce tiny sheath folds, so like this guy and this one. So pretty tiny. This is also an analog experiment done by Rosas in 2002. Oh, that's a good idea. Thanks. And then there are other ideas about development of sheath folds which are not related to simple shear, and then they basically suggest you take a curvilinear fold and just squeeze it and put it under constriction or flattening and get a sheath fold in that way. So the problem a little bit with this whole thing is it is very tricky to observe in nature what exactly triggers the sheath fold. It has two reasons. One of them is the initial perturbation or the initial triggering thing might be very heavily overprinted by the bulk deformation. So we don't see any dent or any pre-existing structure afterwards. Or that the triggering objects, such as the rigid inclusion, might get separated from the resulting fold during the deformation. And then an additional point is that this list I just presented you might not be complete. This whole thing led us to the idea if it is basically possible to produce a sheath fold with a weak inclusion. So what we wanted to do is we're having a slip surface, which is a weak inclusion. That can be a crack or a vein or a weak sedimentary layer or even a mineral, which is embedded in a matrix and put on the simple shear. And we wanted to know if that is enough to produce a sheath fold. So is it enough to perturb the flow in simple shear to have, in the end, such a sheath fold? In case this works, we would like to know, does it matter how we orient this slip surface? Is it possible also to have such a sheath fold if we have a mechanically layered system? And does it matter how thick we choose these layers to be? To address all these questions, we do two things. We are using an analytical model and we do analog experiments. Now, maybe some of you ask themselves, so is it really worth spending 3 years and an entire PhD on sheath folds? Actually, it might be worth, I hope so. And that's because sheath folds are used in the field to indicate shear sense, strain magnitude, and bulk strain type. Now, especially strain magnitude and bulk strain type are things which are relatively hard to put a number onto them in the field. So in case sheath fold really work as indicator for these things would be great. At least they are used for that. Now, the problem with that is a little bit that there exists no really systematic study on what exactly influences the shape of these folds. And that's now where this study should fill the gap at least a little bit. And I want to start with the analytical model. So this model is based on the external Eshelby solution. It has been programmed by Martin, and it basically is a block of a matrix which is linear viscous, isotropic, and incompressible. And in this matrix we have marker layers. So these layers are purely passive. They don't have any kind of property. They just for the visualization. In this matrix block, we then place a slip surface, and this slip surface is almost an almost two-dimensional feature. It is filled with inviscid fluid. It's incompressible. Yeah, and the thing we can vary is basically the shape of this inclusion and the angle it is placed in at the beginning. Then we subject the whole system to simple shear, and while it deforms, this inclusion will rotate into a stable position, or almost, and it will stretch and deform, but it will not propagate. So it is not possible that this inclusion is basically leaving the matrix block. And then our first question is, does it actually work? Can we produce a sheath fold with this model? And that's a picture of one of the experiments, and I guess we can say, yes, it works. So in this experiment, we sheared the whole system to a shear strain of gamma 10. The initial orientation of the slip surface was 135 degrees. So if that's the shear direction, it used to be like that, then it kind of turns during the shear. And the shape of the inclusion was a circle. Now here, the layers are colored, but as I said, they don't have any different properties. It's just coloring to make them visible. We can very nicely see here this cone-shaped structure. If we cut it open, we also see these circles here. This black area here is part of the slip surface, which you can now see is clearly deformed. So it's not a circle anymore, so it got stretched. So to answer this question, I think, yes, we can definitely say it works. Now, to use three-dimensional visualization is always a little bit tricky to extract information. So we decided to cut open the models into cross-sections. So this is now a cross-section which we cut parallel to the shear direction. So for your information, that's the sheath fold, and we cut it parallel to the shear or elongation direction. What you see here is the red line is the inclusion, which got stretched. The black lines are just these marker layers visualizing the deformation in the matrix. Now, if we compare this experiment to what we can observe in nature, kind of looks similar. So you also have a slip surface in here, and you have deformed layers around it. These structures are typically called flanking structures. So for structural geologists, that's something which might be known. It doesn't really look like a sheath fold if we look at it this way. But if we cut it perpendicular to the shear direction, as you can see here, then we see suddenly these closed shapes which are characteristic for sheath folds. That's a natural example, that's our experiment. And it kind of looks reasonably close. So if we then want to investigate the impact of different initial orientations of the slip surface. In this little movie, you see the red thing is the slip surface. The black lines are just visualizing the deformation in the matrix. I quickly run it again. And it goes from strain 0 to 10. So that's just a snapshot at gamma 10. As you see here, like these folds kind of start at the tip of the inclusion. And if we cut the whole system perpendicular to the shear direction, we get this picture, where you see again these closed shapes. So they don't look closed here because I just plotted half of the model because it's mirror symmetric, but they are closed. Now if we put in the inclusion in an angle of 90 degrees, you can very nicely see how the inclusion stretches and rotates. And again, on how these folds start at the tip of the crack. That's a snapshot of it again at gamma 10. It's basically exactly the same. The red line is the inclusion, black line is the matrix deformation. If we cut it again open, perpendicular to the shear direction, we again see these closed contours. So it looks like that the initial orientation of the slip surface has an impact on a little bit the actual shape of the things, but it produces sheath folds in any case. Another thing which we found quite interesting was how does the shape of these cross sections depend on the distance on where we cut the fold. So here the black line, that's a cross section parallel to the shear direction. The black line is the slip surface. The colors are just layers. And if we cut the model relatively close to the tip of the slip surface, we see these closed shapes, but they are kind of not very easy to detect, and maybe in the field nobody would realize that that might be a sheath fold. But then if we move this cutting plane further away from the tip of the slip surface, we see once more these very nicely closed shapes, and it looks really quite pretty and like a sheath fold, like how we imagine it to be. And even if we move it further away, it's kind of similar. However, if we would cut it up here, then we would just see horizontal layers. So we conclude from that the location of the cross section influences the pattern we observe quite strongly. Now, how does our model compare with nature? That's the sheath fold from Opdahl. And if we, for example, follow this pinkish layer, we see that it comes from a horizontal position. It kind of closes all the way and goes into horizontal again. And that's a little bit similar to what this gray layer here is doing. So it comes from a horizontal position, it closes and goes into horizontal. We also have closed contours, like this one, and we have layers which are going around the otherwise closed contour, which are a little bit similar to this one. So it looks like this model basically captures the first-hand observation from the field. Now, if we take exactly the same model and we move the cut a little bit closer to the slip surface and we put in a little bit more layer for better resolution, we suddenly got something which produced two of these closed contours on top of each other. Now, that might at first look a little bit that's weird, but then we found exactly the same thing in nature. From, for example, this sheath fold from Namibia, we can see two of these closed contours on top of each other. If that's a little bit not very well visible, then sure on this sketch it is. So you see two of these eyes on top of each other. So we basically conclude, so first order observation we can capture, and we can also capture the diversity of these layers. So we have all types of layers which are relatively similar in the model and nature. So to conclude, the stuff from the analytical model, first we can say, yes, slip surface can produce a sheath fold. The initial orientation of the slip surface is not very relevant. So it produces a sheath fold anyway. It doesn't matter how we orient the slip surface. But the 2D section, the location of the 2D section really influences the pattern we see. And our model captures first order field observation. Yes?
In the field data, can you infer that the same mechanism for the production of these structures was active? Can you say that you have a slip surface that produces those?
No. The problem is to actually see what exactly triggers the sheath fold in nature is extremely tricky. And if you have a slip surface, that's something which gets extremely stretched and it's pretty thin, and that's almost impossible to see. In addition comes whenever you have a cross sections showing these closed layers, they are basically located away from the slip surface. So in the same cut, you don't see these rings and the slip surface. So one basically would have to have an entire sheath fold, including the slip surface, and then you would have to scan it or slice through it. So far, we just haven't found any. We kind of hope with publishing these things that actually field geologists go out and actively look for these slip surfaces. We'll see what happens. So far, it hasn't happened. So we'll see. Does it answer your question? Good. Okay. Then, however, if we look at a sheath fold like that, we can see that the black layers and the white layers they're not really behaving the same. So the black layers are weathered back compared to the white ones. And it is quite unlikely to assume that they have the same viscosity. So if we want to test what impact the viscosity contrast has on the sheath fold development, we cannot really use our analytical model because we can only have a homogeneous matrix. Now, to investigate the impact of the viscosity contrast, we use experimental models. And for that purpose, I traveled to Rennes, where this simple shear apparatus is standing. So it's quite an old apparatus, like 30 years old, but it works very well and it's able to produce simple shear to quite high shear strains, which is exactly what we need. Now, the experimental setup looks as follows. We have a box containing the experiments, which is 40 centimeters long, 10 centimeters wide, and 5 centimeters high. In this box, we place many thin layers of silicone. In the middle of the whole silicone cube, we place the slip surface, which is basically a cut in the silicone, which we lubricate with liquid soap. So the materials we're using are, for the slip surface, it's liquid soap. That's approximately 1 pascal second. To simulate the rock, we're using PDMS, which is a silicone. And we can vary the viscosity contrast, so we can get a ratio of approximately 50 between 2 silicones. Now, the first thing we tried was, again, to see if also in these experiments the slip surface is the actual trigger of the sheath fold. So we did 2 experiments where we had 2 silicones, the black and the red one, which are exactly the same viscosity, so it's only color difference. These 2 pictures are cross sections perpendicular to the stretching direction. And in the first experiment, we had no slip surface. We subjected the whole experiment to gamma 6, and the layers look like that. So they're horizontal. I mean, we see some small perturbations which are due to air bubbles which were trapped in the model, but I mean, it's definitely not a sheath fold, and these air bubbles are a side effect of the method and are not really, it's not what we wanted. But if we put in a slip surface, then again, we start seeing these closed shapes which are characteristic for sheath folds. So we basically concluded that, yes, the slip surface is the thing which triggers also in these experiments the sheath fold. Now, to investigate the impact of layers, we did 2 series of experiments. In one, we kept the layer thickness constant at 1 millimeter and increased the viscosity contrast. And in the other one, we kept the viscosity ratio constant at 10 and increased the layer thickness. So to investigate the impact of the viscosity ratio, so we increased the viscosity ratio from 1 to 50. In all experiments, layer thickness is 1. That's basically the same picture as before. So it's no viscosity contrast between the two silicons, and you have this nice closed contour. In this case, it's really hard to see, but you have, in this case, maybe to believe me. It's a viscosity ratio of 5, and you see here a closed contour. The experiment was rather tricky, this one. It had lots of air bubbles, which were not really wanted, but we could see that it produced a sheath fold. If we increase the viscosity ratio to 10, we get here a very nice closed contour, which is sheath fold. We got another one here, which was a side effect of an air bubble that was trapped, and we didn't really intend this one, but yeah, can happen. With a viscosity ratio of 20, we got a very nice sheath fold up here. Then with a viscosity ratio of 50, it got a little bit tricky. It produced something like a sheath fold here, and it definitely deformed the layer quite strongly. But the problem was producing these layers was very tricky for such a high viscosity contrast. And we were not able to have them exact the same thickness for the weak and the strong layers. So the thing we can say is that we can have very nice sheath folds in a layered matrix with a viscosity contrast from up to 20. Now, the previous slide was just showing one cross-section per experiment. But there are many, like in one experiment, we get many cross-sections showing these closed contours. So that's basically an illustration of how approximately this sheath fold would look in 3D. This section here represents the last section, which shows still the slip surface. Then all these sections here, they show closed contours and are part of the same sheath fold. This gray area is just a visual aid to show how this sheath fold might look approximately. Now, to get some more information about these experiments, we measured on each of these sections, we measured 3 geometrical parameters, which are the width of this outermost closed contour, its height, and the depth from the top of the experiment. We plotted all these measurements against the horizontal distance of the sheath fold, so for each slide from the crack to the tip of the sheath fold. And we see that the width decreases towards the tip of the sheath fold. I mean, that's not really surprising. We also see that the height is almost constant for the whole length of the sheath fold. We see that all the sheath folds dip into the matrix. And we tried also to plot the ratio between the width and the height, and it makes a rather useless cloud of points. Then the things we could extract from that was that the opening angle, which is basically how narrow this cone is, how this depends on the viscosity ratio. And within the error, it shows that it gets larger with higher viscosity ratios. And we also checked on the length of the sheath fold, and it gets shorter with a higher viscosity ratio, and it dips steeper into the matrix with a higher viscosity ratio. So that's what we more or less figured out on the impact of the viscosity. Now, if you want to investigate the impact of the layer thickness, we did a very similar series of experiments where we kept the viscosity contrast stable at 10. We increased the layers from 0.5 millimeters to 6 millimeters and basically did exactly the same thing. So for 0.5 millimeters, we get closed contours here. That was extremely tricky to see because, I mean, 0.5 millimeter is not really thick, and you got 100 layers in this box. So that's really tiny. And then, but we definitely see sheath fold up here. For a layer thickness of 1, we can have it here, and the one which was not intended here. For a layer thickness of 2, we see the closed thing here, even though it gets already a little bit tricky to really see the closed shape. For a layer thickness of 4 millimeters, we cannot see it at all. We see quite strongly deformed layers, but no closed contour. And for a layer thickness of 6 millimeters, we got one slice, like one cross-section which showed one closed contour, and all the rest looked basically like that one. So the thing we can say is that the layer thickness influences the visibility of the sheath fold very strongly. Now, we did measure exactly the same parameters as before, and the problem is a little bit that for one experiment we just get 1 point. For the first experiments, which was very hard to detect the closed contours, we get a little bit a big error. So if we kind of try to interpolate between these points, we get that the sheath fold actually gets wider towards the tip of the fold, which is obviously nonsense. So that's not really reliable. And the other two show again that it gets smaller, height stays approximately the same. They dip downwards in the matrix, and this cloud of points again doesn't help. Now, if we want to say anything about the opening angle dependence on layer thickness and so on, we get into troubles because we don't really have enough data points, because we cannot produce thinner layers. That's not possible with the method we are using. We cannot make thicker layers because then we anyway don't see a sheath fold. So we basically have to be content with the conclusion that the layer thickness is very relevant for the visibility, but we cannot say anything about systematic dependence. Now, we realized that the 3D shape is kind of an important factor. As we saw with the dependence on the viscosity ratio, it really influences like the overall shape of the sheath fold. So we decided we want to have a better three-dimensional visualization. So that's a picture one of the guys in Rennes produced. He is using GoCut to make these things, and GoCut is a software which is used by the oil industry mostly. And what it does is it interpolates between seismic sections. And instead of seismic sections, we are just using the sections from the experiment and try to interpolate how these layers might look in between the sections. And now I have a very nice three-dimensional PDF on how this approximately looks. So it's just the green surface is like the one layer, and you see how the sheath fold would look in 3D. It's the actual reconstruction of the experiment. So that's kind of a cool tool to play around with. So we should make a movie out of that. Yeah. So at the moment, yeah, we're just checking on how we can use GoCut to make like images like this out of the experiments. Okay, so if we compare our experiments with nature, we can basically see very similar things to the thing we saw before. So this again is my favorite sheath fold from Opdal. And you see again that this gray layer here kind of behaves similarly to the pink one. And again, you also have these closed contours like here. So we can say that we capture again like first order observations. In these experiments, we also can capture things like the thickening of some of the layers. Like for example, this white one, it's pretty similar to this one. Now, the problem is, like, these two pictures are from different experiments with different viscosity ratios. There is, however, no systematic difference between these two things, like cross-section, if we just look at the cross-sections. And we don't know the viscosity ratios between the layers in these natural examples. So, to conclude the things we did in the analog experiments, we were basically the first one who managed to produce sheath fold in a relatively fine layered matrix with a viscosity ratio over 10. And that's rather cool because before, like, people just claimed it's not possible to have that. We can show once more that slip surface nucleate the sheath fold. We see that sheath fold develop in layer matrix with viscosity ratios up to 20. And we see that this viscosity ratio influences the 3D shape of the fold. and we see that the visibility of the sheath fold depends heavily on the layer thickness. Now, if we kind of bring everything together, like the nature, the analytical model, and the analog experiments, we can see that say that in both cases, experiments and analytics, we can capture first-order observations. And we saw in both cases, in the experiments and the analytics, that we can trigger sheath folds relatively easy with the slip surface. Now, we have different initial conditions, such as the slip surface orientation, a viscosity contrast, and to a certain extent also the layer thickness. And all of that leads to the formation of sheath folds. Now, that's it from my side for the moment. And for all of you who think sheath folds are for nothing, I have to inform you that at least the fashion industry has figured out that they're very aesthetical. And thank you very much for your attention.